Let's be honest. Have you ever looked at an organic chemistry textbook and just thought, what a mess? It can feel like this endless, chaotic swirl of letters and lines that just don't follow any rules.
But what if I told you that was all wrong? What if, hidden beneath all of that apparent chaos, there's actually a really simple, predictable logic, a set of rules that governs almost every single reaction out there?
Well, that's exactly what we're going to do. We're going to pull back the curtain and find that hidden logic. By the end of this, you'll have a simple framework to understand and even predict what's going to happen in most organic reactions. No more random guessing, just a clear, logical path.
Okay, so to understand any game, you've got to know the players first, right? In organic chemistry, our main players are called reagents, and they pretty much come in two flavors, all defined by what they're looking for.
On one side of the field, you've got your electrophiles. The name says it all, electron lovers. These guys are electron poor, and they are desperately seeking electrons. Then, on the other side, you have the nucleophiles, or nucleus lovers. They're loaded with extra electrons and are looking for a positive charge to connect with. It really just boils down to who has the electrons and who wants them.
So an electrophile, which we'll call E+, is basically a heat-seeking missile for negative charge. Think of things like a hydrogen ion, H+, or NO2+. They see a spot that's rich in electrons, like the double bond you'd find in an alkene, and they just go straight for it. That's their whole mission.
And a nucleophile, Nu-, is the total opposite. It's swimming in electrons. Usually with these lone pairs, it's just itching to share. So it seeks out atoms that are electron poor, carbons that have a slight positive charge on them. Things like hydroxide, OX-, or ammonia, NH3. They've got electrons to give, and they're looking for a good home for them.
Okay, so just when you think you've got it, chemistry throws in a little twist. Some of these reagents can be versatile. They can act as a nucleophile, like we just talked about, but they can also act as something called a base. So how on earth do you tell the difference?
Well, the answer is actually simple. It's all about the target. A nucleophile is laser-focused on one thing, attacking a positive carbon atom to make a new bond. But a base completely ignores the carbon. It goes for a positive hydrogen atom, a proton, and just snatches it away. Same player, totally different game plan, and it all depends on what it attacks.
So we know our players. Now let's talk about the playing field. In organic chemistry, the field is really just the state of the carbon atom that's about to react. The big question is it a crowded house or is there room for more?
Think of it like a party. A saturated carbon is at max capacity. It's bonded to 4 different things. The house is completely full. If a new guest wants to come in, someone's got to leave first. But an unsaturated carbon, it's bonded to fewer than 4 things. It's got empty space, a welcome mat out for a new group to join without kicking anyone to the curb.
All right, we have our players, we have our field. When they finally come together, one of 3 main moves is going to happen. These are the fundamental reaction types.
First up, we've got substitution. This is the only move available when you're dealing with a saturated, totally crowded carbon. Since there's no free space, the incoming player has to literally replace or substitute a player that's already there. It's a strict one-in, one-out policy. The second move is addition. This is what happens on an unsaturated carbon, where there's plenty of room. Because there's space available, a new group can simply be added on. Nobody has to leave the party. It's not a replacement, it's just a new guest showing up. And finally, our third move is elimination. You can think of this as pretty much the reverse of addition. Instead of adding something to the molecule, we're removing atoms from it. And when we do that, we often create a new double bond, turning a saturated carbon into an unsaturated one. Okay, this is it. This is the moment we've been building towards. We've met the players, we've checked out the field, and we know the 3 main moves. Now, let's put it all together into a simple, powerful tool you can use every time. Believe it or not, it all boils down to just 2 simple questions. First, who's making the first move? Is it an electrophile, hunting for electrons, or a nucleophile, looking for a positive charge? And second, what's the field like? Is that target carbon saturated and full, or unsaturated with room to spare? Answer those 2 questions, and boom, you can name the move.
Let's put this framework to the test. Let's take an alkyl halide. Now the halogen atom pulls electrons away, making the carbon next to it a little bit positive. So what's it going to attract? A nucleophile. That's question 1. Now question 2. How's the field? That carbon is bonded to 4 things, so it is saturated. And there you go. The answer has to be a nucleophilic substitution. See, the framework just leads you right there.
Let's try another one, an alkene. That double bond is basically a big cloud of electrons just sitting there, so it's a magnet for an electrophile. The carbons in that double bond, they're only connected to 3 other groups each, which means they are unsaturated. Put it together, electrophilic addition. It works.
Now, just when you think you have it all figured out, chemistry does what it does best and throws us a curveball. Because just like any game with rules, this one has a few special players that, well, they get to break the rules.
As the source material so perfectly puts it, some molecules just get special treatment. They don't have to follow the rules we've laid out because, hey, VIP is VIP. Let's meet a couple of these special cases.
First up in the VIP lounge is benzene. I mean, look at it. It's covered in double bonds. It's clearly unsaturated, so our rules say it should undergo addition no problem, but it almost never does. And why is that? Because that ring of electrons gives it this incredible, unique stability called resonance. An addition reaction would shatter that stable ring, and the molecule will do anything to avoid that. So to protect its special VIP status, it breaks the rules and undergoes substitution instead.
Our second VIP is the acid chloride. And again, you look at that reactive carbon, it's unsaturated, we expect addition. But its behavior is completely controlled by one thing. That chlorine atom attached to it is what chemists call a good leaving group. It is so stable and so happy to leave the molecule on its own that even though there's space for addition, the molecule just goes for substitution instead, because that chlorine is practically already halfway out the door.
And really, that's the big takeaway here. This simple framework, players, fields, and moves, is an incredibly powerful way to predict how most molecules are going to act. But the exceptions, the VIPs, they aren't just there to annoy us. They actually show us where the deeper, more interesting chemistry is happening. They teach us about things like stability and reactivity that are at the very heart of the subject.
So now you have the framework. The next time you're faced with a chemical reaction that looks like a total mystery, don't panic. Just ask yourself the 2 simple questions. Who are the players and what's the field? Because once you understand the rules, you can start to really appreciate the beautiful game of chemistry, and especially its fascinating exceptions.